All right, so welcome back. In the last lecture, we worked on identifying what we could consider to be crystal structures within metallic systems. Now we're going to investigate these crystal structures a little further. Now, if we really think about the crystal structure in the unit cells, the BCC, FCC, and HCP unit cells that we discussed in a little bit of depth the last time, we can look at these as almost roadmaps. And as we start thinking of a roadmap, we need to find points of interest, directions, which be like almost streets, and planes, which we could consider almost to be blocks within a city grid structure. And so as we start moving forward, we're going to see that an understanding of these is important. Now, in the electronics industry, these are important mostly because materials like silicon and germanium and other things that are widely used in that industry really rely on very specific planes of atoms, or what we consider to be orientations within each of the crystal structures in order to provide the properties that they're looking for. Now, structurally, these points, directions, and planes are also important, but on a much larger scale because they determine where crystalline defects flow, and that allows us to look at plastic deformation and yielding and yield strength and tensile strength, all those mechanical properties that we talked about in the first lesson. So as always, our quote today is again from Edward Teller, and I like this one for the most part because sometimes a hypothesis is guilty until it's found effective. So if you think in terms of what we view as science and engineering, usually we can predict that something may happen, and if it does and it's found effective, it's something that we take as a fact from there. So a nice little quote from Edward Teller. Now today we're going to start talking about single crystals and what they are. We're going to see that they have some fairly unique uses industrially. For the most part, we tend to think of them more in terms of something that might be a bit of a novelty, but almost every high-performance jet engine that you have uses a single crystal at some point. And so moving from single crystals, we're going to start looking at what we call crystallographic directions and planes. And what these are, for the most part, is how we navigate within a crystal structure, is certain directions where the atoms are sitting, where they may be close packed or not, and then planes. And as we move forward, when we get into our next little subchapter here, we start talking about crystalline defects. What we're going to see is an understanding of these are going to be extremely important. We'll briefly touch on linear and planar densities. That's, for the most part, within a given crystal structure, how many atoms are present on one of these directions or planes within the crystal structure. And then we'll move into what close packed crystal structures are. And if we remember from our last lecture talking about the unit cells, there are two primary ones, and that's close packed. The close packed systems are the FCC systems and the HCP crystal structures. And we're going to see how, if we think about them in 3 dimensions, how easily these atoms, if we think of them as hard spheres, can pack together. And we'll hit upon characterization of crystal structures, but typically a little earlier in the lecture than it shows there. So as we move forward, assignments for this week, remember the ones that are the assigned ones are the ones with an asterisk. And so keep that in mind as we move forward. And I recommend, once again, that you do all of the problems that are assigned. And so our important terminology for today and for this lecture is really goes back to that unit cell. A lot of these are the same ones that we looked at before, but I'm going to continue to hit upon the 3 crystal structures that we find most important: face-centered cubic, body-centered cubic, and hexagonal and close packed. Keep those in mind, be able to identify what they look like, because I can just about guarantee that you'll see that on your next exam. So a single crystal. So what is a single crystal? Now, if we start looking at it, it's a periodic arrangement of atoms. And when we think of a single crystal, we can think of some type of perfection, is that it extends over the entirety of the specimen. There's no interruption. All the unit cells interlock in the same way. They have the same orientations. In this one, we see a garnet single crystal. And typically in lecture classes, if we have a little back and forth, I would ask everybody, where are garnet single crystals used? And at this one, what we can sort of see here is how it's faceted. We can see where the cuts are made. And if you look closely enough, you see these lines. Now, those are going to correspond to very specific directions on the crystal. And if we really start thinking about it, these are orientations within the crystal. These are specific crystallographic planes that have been faceted. Now, back to what we would use this type of single crystal for. We would use it traditionally to produce a laser. Neodymium YAG, we call them yttria, alumina, garnet. Crystals are used as a lasing medium for solid state lasers that we use for whether cutting in some cases, welding, cladding, and one of our newer ways of doing things is laser-based deposition and additive manufacturing. So at the core of what we have, at least previously, were these types of small crystals that would be used. They were actually small rods. Some companies use them as a disc, but other companies have gone away from these. But the single crystal was the basis for a lot of the solids, what we call solid state laser technology in the past 25 to 30 years. Now, we see that and we see a practical application of lasers, but one of the more commonly used practical applications for single crystals are in turbine blades. And we haven't gotten to discuss why that is yet, but it has to do with the resistance to what we call creep deformation, which is basically stress at high temperatures. And if we think of a turbine blade, what we have is a condition where we have these blades spinning very rapidly. And what this is a picture, a photograph here of is a row of blades within a land turbine, which is much larger than the jet engines that we may think of. But what is the dominant mechanical or fracture-inducing process within these blades is something called creep. For creep, you need high temperature and high stress areas. And so these blades, when they were initially developed, most everybody tends to think when we think of blades, especially in polycrystalline systems, that we would need an equiaxed crystal structure. What that means is you have a multitude of different crystal orientations, and these are called grains. And what they allow us to do is to produce what we consider to be the strongest material when we think of forged materials. Now, in creep conditions, the existence of these grain boundaries led to premature failures of these blades. So back in the 60s, as people started to want to develop higher performance jet engines, particularly for military jet aircraft, they started needing to look for ways to get around this equiaxed grain structure. And so they started thinking was, well, the grain boundaries are the problem that's leading to the creep issues that we have. And so one way to take it was, let's get rid of the grain boundaries. And in this case, when we think of directional solidification, what we want to do is orient all of these grain boundaries in the orientation where the stress is going to go. So we have anisotropy in our mechanical properties, but that anisotropy we're going to use to our advantage and put it in the orientation where the maximum stress is going to be. Now, with that, there were improvements in performance, but as higher temperatures were required, the existence of even this many grain boundaries was creating problems and decreasing creep lifetimes of the blades. So the solution was to go to a single crystal, to get rid of all the grain boundaries. And we're going to revisit this again, but this is a common use of single crystals, and there are very specialized casting and processing routes in order to produce this type of really single crystalline type structure. Now there's still uniformity there's still long range order, there's everything else that we expect in a crystal structure in this single crystal. It's just that there's only essentially one large grain. Now, I've always asked at this point, sometimes I've put this a little later in the lecture, but for today I wanted to move it up here, is how are crystal structures determined? Now, if we really think about crystal structures, it's not something that we can easily see, because the atoms are in these different planes and orientation, and there's this long-range order of atoms. And if we really think about it, an atom is something that is pretty small. And so with that, how are we able to probe a larger structure with something that allows us to see very small spaces? And the first thing to think about is, let's think about wavelengths. We know light has a wavelength, we know there's infrared, we know there's a whole electromagnetic spectrum where different waves have different wavelengths and they operate at different color schemes in the visible light range and the IR range. They react differently. But in order to really get in between these atoms, we need something with a fairly short wavelength. And so what we find is that X-rays do an excellent job of being able to penetrate these structures, rather small distances into them, but they allow us to be able to identify locations of crystals and actually what those crystals are through what we call characteristic wavelengths. Now, X-ray diffraction is the primary means for determining crystal structure. So we use an X-ray signal and we bombard a solid sample, or in some cases a powder sample, with that X-ray. And as the wavelengths penetrate in, they're going to run into an atom at some point. Now, when they run into that atom, part of that energy is going to be absorbed, but the beam is actually going to reflect off of it, or what we call diffract off of it, at a different angle. And so if we have a detector sitting out here where to capture these diffracted beams, and we know the angle of the incident beam to the diffracted beam, we can determine these angles between these different elements. We know that some of the energy was absorbed during the diffraction, so the wavelength has slightly changed. And knowing that theta angle, knowing that wavelength, we can actually determine what the crystal structures are and what their location is within the crystal structure. So a lot of what we're going to talk about today is based off the use of X-ray diffraction as a tool for determining what the actual crystal structure is. And within that, we can plot out where these different reflections, we call them, may occur. And so at that point, we're able to actually start to map where all of the atoms sit in these different crystal structures.